Hello everyone and welcome back to the channel. Today we are going to kick off with a non-exhaustive series on thermodynamics. To truly understand this field, we have to go back to how it all started. Early scientists once believed that, oh no, not this early. Maybe this is better, maybe around this time. The scientists around this time believed that heat was a physical substance that flowed from hot objects to cold objects. And how they described this particular substance was kind of mysterious. That the substance was a fluid and was invisible, something like air. One thing they noticed about this substance is that as it moved from a hot object to a cold object, it changed a specific property of the objects, which we now know today as temperature, even though they didn't quite have a formal definition of temperature back then. When you were a baby, your mother would normally put her hand on your body to find out your body temperature. And this particular concept suggests that whenever your mother puts her hand on your body transfers some fluid to your mother's hand. The fluid is invisible, and that tells your mother that your body temperature has risen or it has gone down. Caloric fluid was the name they give to this particular substance. The question in your head right now might be something like, wait, what is that? I don't know either. The only description we have of a caloric fluid is that it's a fluid and it's invisible. So I do not know any more than you do. This was known as the caloric theory, and I think I might be spending an unhealthy amount of time talking about it, mostly because it's a dead theory and also because it's phenomenologically misleading in the modern world. Everything changed in the late 18th and early 19th centuries with Benjamin Thompson, also known as Ramford Count. While supervising the boring of cannons for the military, he noticed something strange. The friction from the process generated an endless amount of heat, and he realized something. If the metal had fluid stored inside it, and this fluid was generating the heat, it should eventually run out, isn't it? But that didn't happen. This proved that heat wasn't a fluid at all, but a form of energy in transit related to motion or mechanical work. This discovery gave birth to the study of modern thermodynamics, where temperature became a fundamental property. In the first part of this series, we'll talk about how temperature relates to physical quantities like volume and pressure. We are starting today with the most basic concept. What is temperature? And how do we actually quantify it? I hope you enjoy this journey into the world of heat and energy. You already have an intuitive feeling for what temperature is, the degree of hotness or coldness of a substance. So when you touch an extremely heated metal, you know it's hot and you can report on that. And when you also touch ice water, you know it's cold, so you can also report on that as well. So there is a clear distinction between the very hot and the very cold. But the problem comes in when you look at in between these two extremes. What do you say about that? And also, what about two objects that are almost of the same degree of hotness? How do you report that? Temperature doesn't have a direct way to measure it. So, it's not a physical quantity like mass, length, volume, or any other thing. So how we quantify it is this way. We examine its relationship with the physical quantities that we can measure. And when those physical quantities change, we study the behavior of those physical quantities with respect to the temperature
and we can give a value to the temperature based on the changes. So that's what we are going to explore to understand how hot a body is, to assign a certain temperature to a body. Imagine you have a rod of length L0 and you put it at a place where you think the temperature is low. But since we want to actually quantify temperature, we won't presuppose temperature as a measure. We will say low degree of hotness and high degree of hotness. So you put the initial length at a place where there is a low degree of hotness and a place where there is a relatively high degree of hotness. And then you observe whether there is a change in the rod. If the rod shrinks, then you know that temperature and the rod have an inverse relationship. If the rod expands, you know they have a kind of a proportional relationship. As length increases, temperature increases. We see that the length increases as the temperature increases. So in that case, we know that our temperature is directly proportional to the physical quantity length. And we can write that mathematically as the change in length, which is the final length L1 minus L0, is proportional to the temperature change, which is also T1 minus T2 for some initial and final changes, respectively. Let's say the change in length is represented by the variable E, which can be extension or just change in length. And we replace it in the proportionality relationship. So we find out that we have a directly proportional relationship between the change in length and the change in temperature. Another particular fact we have to know before we proceed is that the change in length, is also directly proportional to the original length. So the longer the rod, the longer the expansion. So if we combine this with the original relationship between the temperature and the length, we will get that the extension or the expansion depends on the product of the original length and the change in temperature. Now it is time to satisfy the mathematical relation with a proportionality constant. And this proportionality constant, let's just call it alpha. Alpha is known as the coefficient of linear expansion because this deals with length. If it is area, then it is coefficient of superficial expansion or coefficient of area expansion. So let's just keep it generic. Coefficient of expansion. So when it's length, then it's linear expansion. When it's area, then it's superficial expansion. When it's volume, it's kind of volume expansion or cubic expansion. So this particular constant only varies from material to material. If the material of the rod is different, then the coefficient of expansion will be different. If it's copper, it's different. If it's aluminum, it's different. That's the only thing you have to note about this. The same thing happens when you want to look at it from the perspective of area expansion. The expansion is also dependent on a certain coefficient of expansion called the coefficient of superficial expansion and depends on the original area and the change in temperature. We already defined the extension as the final length minus the initial length. So this would be equal to this. So in a way, we have found a way to relate temperature, which we didn't know how to measure, to the physical quantities like length, area, and volume. So the same parallel happens in the case of area. In the case where the length is now area, then we have A1 against A0, and the coefficient of expansion there is usually denoted as beta. So this the same game plays there. And again, if it is volume, you have volume final and volume initial. And the coefficient of expansion there is denoted by gamma. So you know how to write your gamma. So all in all, the technique we were trying to invent so that we can measure temperature was that we relate it to a physical quantity and see how the physical quantity will respond to changes in temperature. And we use that to calibrate temperature. So when you read the physical quantity, then you can just know how hot, you can put a measure on how hot the particular object is. So we have length. They are all given by the same formula, but with different parameters. So for length, it's the length and the coefficient of linear expansion. And for the area, it is the area and the coefficient of superficial expansion. For the volume, it's the volume and the coefficient of cubical expansion. When you use the relationships between area, volume, and length, and you do some little approximations, you arrive at the following relations between the particular constants for the different cases. So if they are all made of the same substance, but we are talking about area, volume, and length separately, this is the relationship between the coefficient of superficial expansion and the coefficient of linear expansions. Beta is equal to 2 alpha. And that of cubical expansion is equal to 3 alpha. So you can already guess that the coefficient of cubical expansion is equal to 3 on 2 times the coefficient of superficial expansion. So you can use these relationships. Don't mind my gamma. You can use these relationships to convert from one to the other. For example, if they give you the coefficient of linear expansion and you are supposed to be working with areas, you can easily convert using this. Otherwise, if they give you the coefficient of linear expansion and you are working in volumes, you can easily use this. It's a very good approximation that works for us, and we use it. Okay, so you might be thinking, yes, we are done here. The point is we wanted a way to measure temperature and we have gotten it. But the problem with these solids is that it's hard to get them to expand, and it's also hard to read with the naked eye if you even notice that it has expanded. The other thing is that this is supposed to be the graph of L against change in T. So it's supposed to be a linear graph starting at L-intercept, L0. And the gradient will be the constant, in this case, alpha, times the initial length. The other problem is that this graph for solids sometimes is nonlinear. For some solids, it's sometimes nonlinear. So they are pretty unreliable when it comes to measuring the temperature based off of them. It's hard to read because a 1 degree temperature change will not do anything to them. So maybe you might be measuring 100 degrees Celsius change, which is not reliable because temperature change is really, really small. And you want to measure a very large chance, it won't happen. So this idea has to be abandoned. What other substance can we turn to make this work? The next we can look for is liquids. And liquids do a better job at this than solids. And they are used in thermometers. Liquid and glass thermometers were very popular and they are still in use. So which means they are very relevant and very useful. So let's turn to liquids and see why they are better than solids at this. So while these ones are better than solids in terms of responding to temperature, they also have their limitations. One of the glaring limitations is the fact that liquids can change their states pretty quickly. For example, when you go to temperatures around 78 degrees Celsius, alcohol will already start evaporating. It will start turning to vapor. Maybe you've entrusted to measure a temperature of about 80 degrees Celsius. But let me be clear here. Evaporation doesn't only happen at the boiling point, but I'm only saying that at the 78 degrees Celsius, alcohol starts to boil and it stops changing linearly with the temperature. So we cannot use it to actually predict temperatures like 100 degrees Celsius and beyond. And even the common liquid we have, water, also faces a very big challenge because at 0 degrees Celsius, it will freeze and it will become solid. So there is no way it will expand or contract linearly with temperature ranges in the negatives, temperature ranges that are negatives. It can't expand in those ranges.
In the next video, we'll briefly talk about how liquid and glass thermometers are calibrated, and then go into gas thermometers, which are the most reliable of all the three. The discussion on gases and gas thermometers will then lead us into gas laws, PV diagrams, and laws of thermodynamics. Thank you very much for watching, and I hope to see you in the next video.